What's up guys, it's me Sir Ernest, and today we're going to talk about velocity of a particle moving in a plane in planar polar coordinate system. Now let's recall, if this is for example your Cartesian coordinate system, a particle at this position will have a position vector given by r at time equal to t. And then let's say this particle move like this one, which is part of this path. Okay, so at a later time t, the position is given by r t plus dt. Okay, so the velocity of the particle, the velocity function of the particle along this path, will now be equal to the derivative of the position vector with respect to time. So we know that the position vector will just be equal to r hat in plane polar coordinates. So we just be equal to derivative with respect to time of r hat. Now before we take the derivative, let's analyze first what happens to the unit vectors at each time. So you will notice that at the initial position, the r hat will be in this direction, while theta hat is in this direction. However, at this position, r hat will now be in this direction, and then theta hat will now be in this direction. So you will notice that the position or the unit vectors r hat and theta hat change as the position of the particle change. So that means, unlike your I hat and j hat, the time derivatives of both r hat and theta hat will not vanish. In fact, in order to take this derivative, we have to use product rule. So in this case, the derivative will now be equal to derivative of r with respect to time r hat plus r times the derivative of r hat with respect to time. Okay, so this r derivative with respect to time is just r dot, so this becomes r dot r hat, and then this becomes r times derivative of r hat with respect to time. Now what is now the derivative of r with respect to time? Now going back to the relationship between r hat and the Cartesian unit vectors, so we know that r hat is equal to cosine theta I hat plus sine theta j hat. So that means we differentiate this expression with respect to time. So this now becomes derivative with respect to time of cosine theta I hat plus sine theta j hat. So differentiating cosine theta with respect to time, because theta is a function of time, and that means this will now be equal to negative sine theta times derivative of theta with respect to time, or simply theta dot. This is I hat. Similarly, the second term becomes cosine theta dot j hat. Now this is now equal to theta dot times negative sine theta I hat plus cosine theta j hat. And what is this? This is actually, yes, that's true. This is equal to theta hat. So in other words, r hat is just derivative of r hat with respect to time is just equal to theta dot theta hat. Okay, so placing it in our expression earlier, this becomes theta dot theta hat. Okay, so that means from here, again, velocity is now equal to r dot r hat plus r theta dot theta hat. So here we can express the radial and angular components of the velocity vector. So the radial component, let's call this VR, will just be equal to r dot. So this means that in this direction, how fast the position, the distance between the origin and your particle changes with time. The angular tells you the direction of the particle, how the particle's angular direction change, or angular position changes with time. So this becomes r theta dot. Okay, sometimes we call this angular direction as your transverse direction. Okay, because this is always perpendicular, the angular component is transverse or perpendicular to your radial component. Okay, so that's it. That's your velocity in plane polar coordinate system. And then we're going to discuss this further by getting the acceleration in plane polar coordinates in the next video. So I hope I'll see you guys in the next video. Thank you for watching. See you there.